Dear colleagues, it is really an honor and pleasure for me to present electromagnetic properties of neutrinos on the most prestigious conference for astroparticle and underground physics. I shall give a short introduction to neutrino electromagnetic properties and then discuss laboratory constraints on the most important neutrino characteristics such as the magnetic and electric dipole moments, media charges and charge radio, but also consider effects of neutrino electromagnetic interactions in astrophysics and the corresponding astrophysical probes of electromagnetic neutrinos. In addition, new phenomena recently studied, which are not electromagnetic by their nature, but can mimic or reproduce the results of those of the electromagnetic nature, will be also presented. In this part, we shall speak about new effects in neutrino oscillation studied in our very recent papers. Several years ago, together with Carl Giunti, we published the paper, Neutrino Electromagnetic Interactions, a Window to New Physics, which is still the most complete among recent reviews on the subject. There are also two interesting and useful papers on the neutrino magnetic moments and media charges have been published recent months. In total, our group have 9 presentations dedicated to neutrino electromagnetic properties and related issues here at the TAUP 2021. Well, if we're really sure that neutrino mass is non-zero, then we should seriously approach the question on the electromagnetic properties of neutrinos. The neutrino electromagnetic properties are described by the so-called electromagnetic vertex function lambda. From the demands of the Lorentz covariance and electromagnetic gauge invariance, it follows that the vertex function can be decomposed in 4 form factors. They are the electric, dipole magnetic and electric, and anapole form factors. The hermeticity and the behavior of the electromagnetic current under the discrete symmetry transformations put further constraints on the form factors. And here we see that the Dirac and Majorana neutrinos exhibit quite different electromagnetic properties. Thus, in general, the study of electromagnetic properties of neutrinos provides a tool for determining the nature of a neutrino, whether it is a Dirac or Majorana particle. In general case, the matrix element of the neutrino electromagnetic current can be considered between different neutrino mass states, and in this case, the form factors are matrices in neutrino mass eigenstate space. In the case of neutrino interaction with real photons, form factors reproduce the corresponding neutrino electromagnetic characteristics, such as, for example, the magnetic and electric dipole moments, etc. It is often claimed that neutrino electromagnetic properties and the magnetic moment, in particular, opens a window to new physics. In the standard model, the magnetic moment is 0, but in the case of non-zero neutrino mass, even in the easiest generalization of the standard model, neutrino have non-zero magnetic moment, which is proportional to neutrino mass. Using the cutting limit for neutrino mass, one gets the magnetic moment of the order 10 to minus 19 Bohr magnetron. This value is many orders of magnitude smaller than the present experimental limits. Let us now turn to laboratory experiments and restrictions on neutrino electromagnetic characteristics, which are included in the tables of neutrino properties have been published by the particle data group. Note that up to now, there is no any evidence in favor of non-zero neutrino electromagnetic properties, either from laboratory experiments or from astrophysical observations. Magnetic moments are the most easily acceptable and well-studied theoretically and in experiments among the electromagnetic characteristics of neutrinos. The studies of neutrino electron scattering provide the most sensitive tool for experimental investigation of neutrino magnetic moments. The cross-section gets an additional contribution that depends on the effective neutrino magnetic moment. From the behavior of the standard model and electromagnetic contribution to the cross-section versus the electron recall energy, it follows that the lower the smallest measurable electron recall energy is, the smaller values of neutrino effective magnetic moments can be probed in such scattering experiments. The best world limit on the neutrino magnetic moment from the react experiments has been obtained by the JAMA experiment in the collaboration of GNR and ITEP at the Kalinin nuclear power plant. The upper limit is 2.9 10 to minus 11 Bohr magnetron. New phase of the JAMA experiment, now called NewGen, is running since this year, and new constraints on neutrino magnetic moment are expected to arrive in a few years. The sensitivity to the magnetic moment will be at the level of from 5 to 9 times to 10 to minus 12. The first results on NuGen are reported here at the TAUP conference by Alexei Labashevsky. That is why I skip those two slides. It is important to note that the measured or constrained value in the scattering experiments is indeed an effective magnetic moment, which depends on the neutrino flavor composition in the detector. Implications of the neutrino magnetic moments limits from different experiments, the reactor and solar, for instance, are in general different. The recent and comprehensive analysis of neutrino electron scattering is given in our paper with Konstantin Kuzakov. In 2017, the Baroxena collaboration from the solar neutrino fluxes also obtained the limit on neutrino magnetic moment, that is 2.8 times 10 to minus 11 Bohr magnetron. Here is a summary of the reactor, accelerator, and solar neutrino limits on the neutrino magnetic moment. These results are quoted by the particle data group. Indeed, it is not excluded, there are corresponding theoretical models, that neutrinos have non-zero electric Milli charge. Some years ago, I analyzed the JAMA collaboration experimental data on neutrino electron scattering and obtained the upper limit on neutrino Milli charge on the level of 1.5 10 to minus 12 charge of electron. This limit is included to the table of neutrino properties by the particle data group. A more stringent limit on Milli charge is expected soon when new data from the running NuGen experiment at the Kalinin power plant will be available. This is a summary of constraints of neutrino Milli charge. In fact, neutrino charge radio are probably the most accessible for observation in laboratory neutrino scattering experiments among the electromagnetic properties. In our already mentioned paper, we have shown in particular that the neutrino charge radius in neutrino electron scattering can be considered just a shift of the vector coupling constant, but there are also contributions from the flavor transition charge radii. Taking all these into account, we, together with our Chinese and Italian colleagues, using the data from the coherent experiment, have obtained for the first time bounds on the neutrino transition charge radio. These results were included to the review of particle properties and also highlighted by the editors of SFD as important results published in the journal that year. Note that the studies of the coherent neutrino scattering provide a very powerful tool for getting constraints in other new effects in fundamental physics. Here is a summary of experimental constraints on neutrino charge radio. Next, we will consider the expected most characteristic consequences of the indicated neutrino processes and the corresponding constraints on the electromagnetic properties of neutrinos which arise under astrophysical conditions. There are several types of neutrino processes which are possibly under condition of non-zero electromagnetic characteristics of neutrinos. I will cite only the main ones which are of interest for astrophysics. First of all, there is a radiative decay of a heavier neutrino into a lighter one. A similar diagram describes the Cherenkov emission of a photon, or more precisely a plasma, when a neutrino moves in a dense medium or in an external magnetic field. Formally, a similar diagram corresponds to the spin light of neutrino in a medium. In the latter case, the electromagnetic radiation arises due to the precession of neutrino spin during the propagation in a medium. Further, due to non-zero dipole moments or Milli charges, the process of decay of a plasma into neutrino-antineutrino pair in dense medium is possible. The process of electromagnetic scattering of neutrinos on electrons, neutrons, and protons is also possible. And finally, the process of interaction of neutrinos with an external field, as a result of which a precession of the particle spin occurs. We have for the first time predicted a similar precession of neutrino spin in the process of interaction of neutrino with the transverse matter currents. The spin light of neutrino in matter, a new mechanism of electromagnetic radiation of neutrinos, was predicted and studied in our papers. In one of our recent papers, we investigated various aspects of the spin light of neutrino in astrophysical environments. Astrophysical bounds on neutrino magnetic moments. One of the most important astrophysical consequences of neutrino magnetic moments is the appearance of nearly sterile right-handed neutrinos. This can be implemented through three different mechanisms. The first is the neutrino helicity change, scattering on electrons, protons, and neutrons. Then the spin flavor precession and oscillations in the transversal magnetic field, and also spin precession in the transversal matter current. Note that the important consequences of neutrino Mealy charge in the neutrino is the neutrino deviation from rectilinear trajectory. The upper limit on the Dirac neutrino magnetic moment on the level 10 to minus 12 Bohr magnetron has been obtained from the observed pulsar duration of neutrinos from supernova 1987. The same limit comes from the absence of the anomalous high-energy neutrinos from a supernova. A more definite limit on neutrino magnetic moments is provided by observations of luminosity of ray Janes. The neutrino magnetic moment plasma decay can influence the observed luminosity of the star, which is constrained by observations. This can be translated to the astrophysical limit on neutrino magnetic moment at the level 3 times 10 to minus 12 Bohr magnetron. There are limits on the effective neutrino magnetic moments from neutrino radiative decay, the process that can be constrained by the absence of decay photons. Astrophysical bounds on neutrino Mealy charge. There are limits from red giant cooling of and neutron star and supernova 1987A. Of course, the most strictly bound to neutrino magnetic neutrino Mealy charge follows from charge neutrality of neutrino and hydrogen atom. There is also quite strong upper bound on neutrino Mealy charge from the effect of neutrino energy quantization in rotating magnetized stars. We have solved the quantum problem of Mealy charge neutrino motion in a magnetized rotating star and have found that neutrino energy is quantized as for the case of an electron in a magnetic field. Within the quasi-classical treatment, it means that neutrino is moving on a circular orbits inside the star under the influence of the effective Lorentz force. Taking into account this effect, we, together with my student Ilya, introduce, as we call it, the neutrino star turning mechanism. The escaping neutrinos are moving on curved orbits inside the star, and the effective Lorentz force should disturb the initial star rotation. In order to avoid the contradiction of the neutrino star turning mechanism packed with the observed data on pulsars, we obtain a stringent limit on the neutrino Mealy charge at the level of 1.3 10 to minus 19 charge of an electron. This is indeed the best astrophysical limit on the neutrino Mealy charge. Now, a few words on the recent new developments in neutrino spin and spin flavor oscillations in magnetic fields and moving matter. It is really exciting that neutrino spin or spin flavor oscillations can be engendered without any magnetic field or magnetic moment of neutrino, but as a result of weak interactions of neutrinos with the transversal matter current or transversal matter polarization. This effect, the effect of neutrino spin oscillations in the transversal matter current, was predicted in my paper of 2004, where the corresponding spin oscillations probability in the transversal current of matter was calculated for the first time. The effect of the helicity conversions and oscillations induced by the transversal matter currents has been recently confirmed by a group of people in their studies of neutrino propagation in astrophysical media. And in this our paper with my student Pavel, we provide a detailed study of the discussed effect, and we investigated different possible resonances in neutrino spin and spin flavor oscillations in the transversal matter currents with consideration of several astrophysical applications. Another interesting phenomenon has been considered in my recent paper with my student Artem. We considered the neutrino flavor and spin oscillations in a constant magnetic field and have found that there is an interplay of flavor and spin oscillations, so that, for example, the amplitude of flavor oscillations on vacuum frequency is modulated by the magnetic frequency. A similar effect exists also when the spin oscillations are engendered by the transversal metric currents. In one of our recent papers, we have studied the role of the CP violating phases in neutrino antineutrino oscillations in a magnetic field and dense matter, and shown that the Majorana CP phases induce new resonances. The detection of supernova neutrino fluxes in the future experiments, such as Juno, Dune, and Hyperkamiokande, can give an insight into the nature of CP violation and consequently provides a tool for distinguishing the Dirichlet-Majorana nature of neutrinos. Conclusions. Here is a summary of neutrino electromagnetic properties, both on the theory and experiment. Future prospects. New constraints on neutrino magnetic moment and Milli charge are expected from the JAMA-2 New GAN experiment and probably from Bruxina. Since recently, the liquid xenon detectors have been used to constrain neutrino electromagnetic properties. The recent indication of xenon in favor of non-zero neutrino magnetic moment on the order of the Bruxina limit should be checked in another experimental setup. New improved upper limit from the stellar evolution data for Omega Centauri is 2.2 times 10 to minus 12 Bohr magnitude. Even better limits come from the recent new analysis of the tip of the ray Jane branch. Recently, we have proposed a new experiment with tritium antineutrinos that will be sensitive to neutrino magnetic moment on the level of few times to 10 to minus 13. This is less than all present astrophysical bounds. And finally, recently, X-mass collaboration set new limits on different flavor neutrino Milli charges. The studies of neutrino electromagnetic properties are indeed very important because it is the investigation of properties of an elementary particle, and also it provides an important insight to fundamentals of particle physics. Thank you